Hello, welcome back to 15-Minute Math. So we went over the first derivative test, and remember the first derivative test can tell us where minimums and maximums lie, and more so it tells us which of our critical points are minimums, which of our critical points are maximums. And the second derivative test is actually another way to do the same thing. We can still find out which of our critical points are minimums or maximums, but first I think we need a little bit of an intuition of what the second derivative of a function tells us. I know in an earlier video we covered how to find a second derivative or how to find higher order derivatives, but we really didn't go into real big detail, what does this really mean as far as our function is concerned. And so let's refresh our memory on what the derivative really tells us. So if I have a function f, so consider function f, and we'll say f of x. We'll use our variable x there. F prime of x gives the rate of change of the function. Remember, that's telling us how quickly or slowly the function is changing. It's the rate of change. Or another way to say that is the slope. Okay, and f double prime, our second derivative, I'm going to say it kind of in a weird way first perhaps, is the rate of change of the rate of change. Or the slope of the slope. The rate of change of the rate of change. Maybe I should add of f, of the original function. And to see what I mean by that, let's go over to Desmos real quick. And so I've got this parabola here. You can see it's just x squared, very plain Jane. And let's maybe try to sketch out the first derivative. And so what I'm going to do is I'm just going to sample a few points, and maybe I'll start at -2. So -2, if I drew a tangent line here, it's going to be somewhat steep and negative. That's not a very good tangent line. Let's try again. Somewhat steep and negative. So maybe we'll just put the point, well, it's going to maybe be off our screen. Just at the very bottom, maybe. We're very qualitative here. And then at 1, notice at 1, it's kind of less steep, but it's still negative. So we're going to have a smaller negative number. Well, I should say a smaller in magnitude negative number. And so maybe we'll put it something maybe over here. And then at 0, notice the slope is 0. And so we'll have a point here. And then things are going to kind of be symmetric. It's a parabola. Parabolas are nice and symmetric. And so notice that the slope here is the same in magnitude as the slope there. It's just positive now. So we'll just kind of have, in fact, this looks like, honestly, a pretty good point for not only f, but also f prime. And then at 2, again, it's, same magnitude as over here. It's just positive now. And so maybe we'll just put it like right here. And so you can see this is forming, yikes, I'm not very good at drawing a line, but it's kind of forming a line. There we go. And of course, we know that if f of x is x squared, then f prime of x, just by the power rule, would just be 2x. And so we just get a line with a slope of 2. Which is what we see here, just kind of qualitatively sketching out tangents. So that's the first derivative. Now, how could we come up with the second derivative? Well, we just do the derivative of the derivative. And so we're just thinking, what's the slope of this line at various points? And of course, the slope of this line is always 2. We knew it from the power rule, but even just looking here, we could always say, okay, well, the slope's going to be constant. It's a line. It's just a matter of figuring out what that constant slope is. And so f double prime kind of looks like this. So f double prime describes how the slope of the derivative is changing. So I'm just kind of labeling my graphs here. And in this case, the slope of the derivative is constant. The slope of the derivative does not change, and so you see that horizontal line there. I want to be a little more qualitative, and when I'm on Desmos, I feel kind of obligated to get my numbers right. Oh, we don't want inventor. So I'm going to go back to the whiteboard here. I have to clear off there we go. And we're just going to qualitatively draw a graph, and we're just going to talk about the second derivative of that graph. Okay, let's say f is in green here. All right, something like that. There is f. And so let's see. Let's look at, just kind of from left to right, I suppose. And let's talk about the derivative of the function as we go along. So the derivative at the very far left is going to be big and positive, right? If I drew a tangent line, we would have a big positive number as the slope. And then as the derivative, as we go towards the right and we cruise along our function here, the derivative is going towards 0. So the derivative is decreasing. And in fact, even once we get to 0, and when I say 0, I mean a derivative of 0, not a function value of 0, or an x value of 0. We're talking specifically the derivative is 0, about where I made that red point. Even there, the derivative continues to decrease, right? We go from big and positive here down to 0, and then we go negative. So we continue to decrease until we get to somewhere in here, maybe. Try to draw maybe a dotted line. Yeah, not great. There we go. And why I say that's my dividing line, because it seems like here I'm at my steepest negative point here. That's where the slope of the graph is the steepest and the most negative. And then as we progress further, our slopes are getting less and less negative until we get to about that point. And then, of course, it's 0, and then they start to increase again. And so over here in this region, f prime is decreasing. And then in this region, f prime is increasing. So when I think about a second derivative, it's really telling me where the derivative is decreasing or where the derivative is increasing. So what this means for my second derivative, it's negative. So if f prime is decreasing, that means f double prime is negative, and if f prime is increasing, f double prime is positive. But if we let a function, or I should say if we let the function's derivative decrease for long enough, it's always going to form this familiar shape. And so there's like a little mnemonic we can say here. If f double prime is negative, our function makes a sad face. That means that f prime is decreasing over that interval. And if f double prime is positive, we're going to have a happy face. So we can kind of just tell by looking at a graph, what regions the second derivative is positive and what regions the second derivative is negative. By the way, there is a name for this. If f double prime is negative, we say that the function is concave down. Which, sad face, you can kind of see it. It opens downward. And then if f double prime is positive, we say the function is concave up on that interval. And so just like using the first derivative, we can tell where the function is increasing or decreasing. We can use the second derivative to tell where the function is concave up or concave down. And with that understanding, I think we can now start talking a little bit more intelligently about this second derivative test. Because think about this. If I have a critical value or a critical point, let's say that's the critical point I wanted to look at. If that critical point just so happens to lie in a region that's concave down, which is to say f double prime is negative, that's got to be a maximum, right? I mean, just think about sad guy here. If there's a critical point, it's got to be this point right here, which is sitting at a maximum. So if a critical point happens in a region where we're concave down, that's got to be a maximum. And if it happens in a region where we're concave up, just kind of by the, same logic, but just the exact opposite situation, that's got to be a minimum, right? And so we can use that to our advantage. Maybe we should write that down. If a critical point occurs in a region that is concave down, that implies it's going to be a maximum. And let's do this. We'll just, in red, we'll say concave up implies minimum. So instead of finding the first derivative and then using our critical points to divide the number line into regions and then testing those regions, we can kind of save ourselves a little bit of hassle. If the second derivative is relatively easy to find, we could just find the second derivative. We can just look, is my critical point in a region where the second derivative is positive, or is it in a region where the second derivative is negative? And that's going to tell us, kind of what's going on with our critical values. And we're going to do a real quick example to end the video, but we're going to do a part 2 where it's nothing but examples, because I know one example maybe isn't quite enough for some people. All right, let's see here. Example, find all relative extrema for f of x equals 1/3 x cubed minus x squared minus 3x. So we're going to use the second derivative test for this. So what we're going to do is, first of all, we need to know what our critical points are. So we still do need to find the first derivative. So let's go ahead and find the derivative. That would just be x squared minus 2x minus 3. Let's find the critical points by setting that equal to 0 and solving. Luckily, this is factorable. I think it factors into minus 3 plus 1. And so we get x equals 3 and negative 1. So those are my two critical points. The question is, are those critical points minimums, maximums, or perhaps neither? So in order to answer that question, let's find the second derivative. And since this is a polynomial, the second derivative is pretty trivial to find. We're just going to do the power rule again. We'll get 2x minus 2, it looks like. Yeah, 2x minus 2. So if I want to find where this changes concavity, I can just set it equal to 0. And I can find where the 0 point is, and then of course anything on one side of the 0 would be positive, and anything on the other side of the 0 is going to be negative. So let's solve 2 equals 2x, x equals 1. So my inflection point, by the way, vocab here, a point where the second derivative is 0, we call that an inflection point. I guess I should be careful with my words here. A point where the concavity changes is an inflection point. This actually turns out to be an inflection point, but just because the second derivative is 0 there, that does not necessarily mean it's an inflection point, because let's say the second derivative is positive on both sides, then it wouldn't change concavity necessarily. We'll see one of those in the next video, but for now, this is an inflection point. And here's how I know this is an inflection point. Let's test a value in the second derivative that's less than 1. Let's test f double prime of 0. If I put in 0, I get a negative number, which means negative infinity to 1 is a region of where it's concave down. So we're concave down on this interval. And f double prime, let's test another number that's bigger than 1. 2. Well, if I put in 2, I get a positive answer, which means from 1 to infinity, we're concave up. So remember, concave down, sad guy. Concave up, happy guy. Which means any critical point in this region is going to be a maximum. Any critical point in this region is a minimum. So what's this mean? Negative 1 is in this region. So negative 1 is a maximum. And then 3 would be in this region. So x equals 3 is a minimum. And I know that just from the concavity. So we're out of time. We're over time. For more examples, check out part 2 of the video.